Hi folks! The following video is going to introduce kinetic isotope effects. Kinetics experiments alone and rate law determination can tell you which reactants and how many of each of them are involved at or before the rate determining step. However, kinetics alone cannot tell you exactly which bonds are being broken, which bonds are being formed, or how atoms are undergoing rehybridizations during the rate determining step. Kinetics alone cannot tell you these things, but isotope effects can. Isotopes are different forms of an element that have the same numbers of protons and electrons, but different numbers of neutrons. If you change out one isotope for another, as either a part of a bond that's changing in a reaction or nearby the bond that's changing, you'll typically observe a change in the rate of a reaction. Most commonly in organic chemistry, we're going to be looking at swapping out a hydrogen for a deuterium. Kinetic isotope effects, also known as KIEs, are a ratio of rate constants. In the numerator is the rate constant with hydrogen, and in the denominator it's the rate constant with deuterium instead, in the case where you're looking at a hydrogen versus deuterium kinetic isotope effect. To get the kinetic isotope effect, you usually have to run two separate experiments to determine these rate constants independently. For the hydrogen sample, you would use just a sample that has the natural abundance of your hydrogen versus deuterium isotopes. The natural abundance of deuterium is 0.015%. For the deuterium sample, to determine the rate constant with deuterium instead, a chemist would either need to synthesize this sample, deliberately putting in deuterium, or they would need to buy this sample, which could be quite expensive. The boring variation of a kinetic isotope effect would be if the kinetic isotope effect is exactly equal to 1. There are two reasons that this might be the case. One is that the bond to hydrogen or deuterium is not changing in the rate determining step, and it's also not near any bonds that are changing in the rate determining step. Alternatively, it's possible that your measurements in the lab just simply aren't accurate enough, and the kinetic isotope effect isn't exactly 1, just really close to it. The more interesting scenario is if the kinetic isotope effect isn't equal to 1. Some definitions to keep in mind for kinetic isotope effects are that we'll call an isotope effect normal if the lighter isotopic isomer reacts faster. I'll also use the term isotopomer to describe the isomer where the isotope is changing. So for a normal kinetic isotope effect, your rate constant with hydrogen would be larger than the one with deuterium, making the kinetic isotope effect greater than 1. We'll call a kinetic isotope effect inverse if the lighter isotopomer reacts slower than the heavier isotopomer. This would be the case if your rate constant with hydrogen is smaller than the rate constant with deuterium, making that ratio of rates, your kinetic isotope effect, less than 1. We'll describe a kinetic isotope effect as primary if the bond to the isotope is breaking or forming in the rate determining step. An example of this is, let's consider an E2 reaction, where the beta hydrogen or deuterium is being deprotonated in the rate determining step. You could measure the rate for this E2 reaction where you had a hydrogen at this position, and then separately measure the rate if you had a deuterium at this position instead. The ratio of these rate constants would give you your isotope effect. We would call this a primary kinetic isotope effect because the bond to the isotope, either hydrogen or deuterium, is being broken in the rate determining step. Primary kinetic isotope effects will always be normal kinetic isotope effects, meaning the KIE would be greater than or equal to 1. We'll call a KIE secondary if the bond to the isotope isn't breaking or forming in the rate determining step. As an example, let's consider the following SN2 reaction. The isotopes that I'm changing are attached to the carbon and could be either a hydrogen or a deuterium. In the SN2 reaction, the nucleophile is attacking carbon and the leaving group is leaving carbon, but the hydrogen or deuterium remains attached to the same carbon throughout the reaction. Because this bond isn't breaking in this reaction, we would describe the isotope effect we measure as secondary. What we'll see in a future video is that secondary kinetic isotope effects could be normal or inverse, meaning they could be greater than 1 or less than 1. For the remainder of today's video, I'm going to be talking exclusively about primary kinetic isotope effects, which will always be greater than or equal to 1. The reason why kinetic isotope effects exist has to do with the vibrational modes for molecules. Let's think back to what we learned about this in the context of IR spectroscopy. So let's consider a bond between A and B. And when we're considering bond vibrations, we're going to think about these as atoms connected by a spring. The following is the equation we used in IR spectroscopy that relates to the frequency of a bond vibration. Nu is the frequency of vibration. The F term is the force constant having to do with the bond strength. And in the denominator we have a reduced mass term, which is defined by multiplying the masses of the atoms in your bond by each other, and then dividing that by the masses of the atoms added together. So let's consider we want to look at the vibration of a CH bond compared to a CD bond. Deuterium is twice as heavy as hydrogen, so it would have a larger reduced mass. Because the reduced mass appears in the denominator, the heavier your mass becomes, the lower the frequency becomes. We'll think about what's known as the zero-point energy, or ZPE, which is the lowest energy vibrational state for your bond. The zero-point energy is equal to 1/2 of h times nu, where h is Planck's constant and nu is your frequency of vibration. Because of deuterium's heavier mass compared to hydrogen, nu would be lower for deuterium compared to hydrogen. This means that the zero-point energy for a bond to deuterium is less than the zero-point energy for a bond to hydrogen. Here I'm considering bonds to the same type of atom, carbon, and imagine these are the same hybridization of carbon as well. Let's consider the homolytic cleavage of a carbon-hydrogen bond compared to a carbon-deuterium bond. This is going to give us our maximum primary kinetic isotope effect. Let's consider a graph of energy with respect to the distance of the carbon-hydrogen bond, or the carbon-deuterium bond, essentially the bond length. The lowest point in energy is where you have your typical bond length, neither too short nor too long. If you go shorter than this typical value, your energy increases because your nuclei repel each other. And going longer than this typical bond length goes higher in energy as well, and you plateau on this side. At this large distance between your carbon and hydrogen or deuterium, this corresponds to having a completely broken bond and having radicals present. On top of this diagram, let's consider what I called the 0-point energies for carbon-hydrogen versus carbon-deuterium bonds. These are our lowest energy vibrational states. This is lower for deuterium compared to hydrogen because deuterium is heavier than hydrogen. Let's consider how much energy it takes to break either our carbon-hydrogen bond or carbon-deuterium bond. I'm comparing the 0-point energy to the energy at which the bond is completely broken. Notice that the difference in energy is larger for deuterium than it is for hydrogen, because deuterium is lower in energy than hydrogen. We could use IR spectroscopy data to estimate the difference in 0-point energies for a CH versus carbon-deuterium bond, and then calculate what our maximum kinetic isotope effect could be. From IR spectroscopy, looking at sp3 hybridized carbons, the frequency of a carbon-hydrogen bond vibration is about 3,000 inverse centimeters, and the frequency of a carbon-deuterium bond vibration is about 2,100 centimeters. It's lower for the carbon-deuterium bond due to the larger reduced mass. The difference in frequencies is about 900 inverse centimeters. From this difference in frequencies, we could calculate a difference in 0-point energies for CH versus CD bonds, and we could relate this to a hypothetical kinetic isotope effect. I won't show the math here, but you could estimate this isotope effect as being e to the power of your difference in 0-point energies divided by RT. Using the difference in frequencies of 900 inverse centimeters and plugging everything in, your maximum primary kinetic isotope effect would be about 7. For reactions in which we aren't having a complete homolytic cleavage of the bond to hydrogen or deuterium, we have to think about 0-point energies for both the starting material as well as the transition state. You can see how this is going to complicate things. So let's imagine a reaction coordinate diagram where we have a single transition state for an endergonic reaction. For the starting material, we can think about different lowest energy vibrational states known as 0-point energies for hydrogen versus deuterium. It's always lower for deuterium compared to hydrogen because of the larger reduced mass. At the transition state as well, we also have differences in energy for hydrogen versus deuterium bonds. So we can think about a difference in 0-point energies between hydrogen and deuterium for both the reactant as well as differences at the transition state. For reactions where you have a primary kinetic isotope effect, this difference in 0-point energies at the transition state is going to be smaller than it was for the reactants. The reason for this is somewhat complicated, but it has to do with accessible vibrational modes at the transition state compared to the reactants. In a case where your difference in 0-point energies is smaller at the transition state compared to the starting materials, the kinetic isotope effect is going to be greater than 1. The reason for this is that it takes less energy for the hydrogen to get up to the transition state than it does for deuterium to get up to the transition state. Think about hydrogen being higher in energy to start by a significant amount, and then it's closer in energy to the transition state, which it needs to get to. Because the barrier is smaller for hydrogen, the rate for hydrogen is larger, and the kinetic isotope effect gets to be greater than 1, because the numerator is larger than the denominator. Depending on the relative energies of the starting materials and intermediate or products, you could have different kinetic isotope effects. And the more symmetric the transition state, with bonds equally breaking and forming, the larger your kinetic isotope effect is going to be, to that maximum value of about 7. Let's consider an acid-base reaction where we have a base deprotonating either a bond between an acid and hydrogen or the acid and deuterium. Let's consider a fairly thermoneutral reaction where the starting materials and products are pretty equal in energy. At your transition state, you'll have pretty similar amounts of bond breakage and bond forming. I would call this a symmetric transition state. When this is the case, the 0-point energies at your transition state are going to be very close together, and they're going to be further apart in your starting material. The energy needed for hydrogen to go from the starting energy to the transition state is smaller than the amount of energy needed to go from deuterium to the transition state. When this is the case, the kinetic isotope effect is going to be relatively large, and it will vary between about 2 and 7. Now let's consider an exergonic reaction, where the products are lower in energy than the starting material. In this case, the transition state is closer in energy to the starting material compared to the product. So by the Hammond postulate, the transition state will more resemble the reactants rather than the products. I can reflect this in the transition state by having the AH bond only slightly broken and the hydrogen B bond only slightly formed. In the case where you ran this reaction with deuterium, you would have a D here instead. Because the transition state resembles the reactants, the 0-point energies in the transition state are going to be more similar to those in the reactants, rather than being very small. In this scenario where you have a fairly large difference in 0-point energies at the transition state, hydrogen doesn't have as much of an advantage compared to deuterium. The rates of reaction for hydrogen versus deuterium will be more similar, and the kinetic isotope effect will be smaller, more like between 1 and 2. The last scenario worth considering is if we have an endergonic reaction step, where the product or intermediate is higher in energy than the reactant. In this case, the transition state will more resemble the intermediate or product compared to the reactant. I would show this by making my bond from A to hydrogen or deuterium long, and the HB bond has nearly formed, meaning it's shorter. For the starting material as well as the product, we would expect a fairly large difference in 0-point energies between hydrogen and deuterium. So I've shown these as fairly separate lines. Because the transition state resembles the products by Hammond's postulate, there will still be a substantial difference in 0-point energies between hydrogen and deuterium at the transition state. Here as well, hydrogen doesn't have as much of an advantage getting to the transition state compared to deuterium as it did in the thermoneutral case, because there's still a significant difference in energies present at the transition state. So we would expect a fairly small kinetic isotope effect. Here as well, this would be about 1 to 2. The takeaway here is that for thermoneutral reactions, in which you have pretty symmetrical bond breaking and forming, you'll have very small differences in 0-point energies at the transition state, whereas in the other scenarios, this will not be the case. The more you minimize the 0-point energy difference at the transition state, the larger your kinetic isotope effect will be, up to that value of about 7. So, in summary, today's video started to talk about kinetic isotope effects, looking at different rate constants for different isotopes. I gave you some terminology related to isotope effects, and then I talked about primary kinetic isotope effects, which involve your bond to the isotope breaking at the transition state. For these primary kinetic isotope effects, we will expect to see normal values ranging between 1 and 7. That's it for this video. I will see you in class.